kinematic function. So anyhow, I think all of you are pretty clear with that part. So we will do, to start with, we will do some, actually this session 3, is it?
So what is coming in the major test?
One-dimensional kinematics, up to one-dimensional kinematics. Okay, but it will be inclusive of what is going to happen in tomorrow's lecture also. I mean, this week's lecture. Yeah, this is kinematics 3. That's correct. Okay. Though I might actually get into projectile motion in the next lecture, but that will not be coming in the major test. Only up to motion along a straight line. Okay. So today we will do some general applications of motion along a straight line. Okay, so by general applications, I mean a situation where we can have variable acceleration also, not just uniform acceleration. So uniformly accelerated 1D motion we have seen a lot of. Okay, only one special case of it we'll start with, that is vertical motion under gravity. Under the action of gravity. So of course, here when I talk about vertical motion, I mean in this particular case that the displacement from the surface of the earth is not of the order of, let's say, hundreds of kilometers, or at least not thousands of kilometers, because then the value of acceleration due to gravity starts to vary, because the earth's diameter is or the earth's radius is about 6,400 kilometers, if I'm not mistaken. So the moment we start going to a distance from the surface of the earth which is of similar order of magnitude, that is, it is comparable to the earth's radius, like it might be 1/2 or 1/3 or even less than that, but it's comparable. So let's say 1,000 kilometers or 500 kilometers plus, then the variation of acceleration due to gravity starts to come into play, because the distance from the center of mass of the earth becomes large enough that there is a weakening of the gravitational force. So then it is no not assuming in this case. So when we are talking about vertical motion or even projectile motion in the next section, what we will be assuming is that we are at distances which are very small distances from the earth's surface, which are very small compared to the radius of earth. Okay, so the distance might be something pretty large, like 100 kilometers also from the earth's surface, but compared to radius of the earth, which is about 6,400 kilometers, 100 kilometers is still very small. It's 1/64. Okay, so what will happen is the value of acceleration due to gravity which we, as you know, commonly denote with the symbol small g, is constant. That means it is independent of height, or for that matter, depth also below the surface of the earth. So that is one assumption that we are doing in this part, as well as in projectile motion. The other assumption we'll be doing is that only gravitational force, what we commonly call weight, okay, acts on the moving object. So in other words, things like air drag, or sometimes you also call viscous force, because of the property called viscosity. So viscous force is negligible basically. There will always be some air drag, but it is negligible compared to the weight. So this is true in the case of an object like, let's say, a metallic object or a stone or something. When we throw it in the air drag is quite negligible compared to this thing, unless we give it spin, and then of course there is Magnus effect and all that. Those are some different things, more complicated things. We'll talk about that later. But like an ordinary stone or a brick, if you drop it from the top of a building, as it is falling, the weight is many times larger than any kind of air drag force acting on it. So you can neglect the air drag force altogether. But at the same time, if you have something like an object made of cotton wool, like a cotton ball, or you have something even lighter like a feather. Now the thing is, it's not that the feather doesn't have weight, it has weight, but the air drag force on it is like comparable to its weight. In certain cases, because of wind resistance, air drag force can become larger than the weight. So its motion is highly influenced by the drag force compared to something like a brick. When you drop it from a height, it's not influenced by drag force at all. So in this particular chapter, when we're talking about vertical motion under gravity, we will assume that we are not taking into account any force apart from gravitational force. And that too, the gravitational force is with uniform value of G. So these two are the important assumptions. Now, once we do this, we understand that it's a case of uniformly accelerated 1D motion. Okay. So therefore, it's evident that okay, it's 1D motion with uniform acceleration. Okay. With the above conditions. The above conditions are in place. That is, the distance we are talking about from the surface of the earth is not comparable to the radius of the earth. It's very small. And the other thing is that we can neglect any other force apart from gravitational force, like air drag or viscous force. Then we are fine with this assumption that it is a one-dimensional motion with uniform acceleration. Okay. So having understood the conditions under which we are doing this discussion, now let's move forward and let's see. It's very simple. So the first case is free fall, which is like the easiest thing you can think about. So if, let's say, from a certain height above a horizontal level, okay, and that too we will take free fall starting from rest as our first case. So let's say a person just drops an object. So a ball or an object is just dropped. That means it's not given any initial momentum, okay, at time t equal to 0. So what happens in this case is, because it will go down because of gravity, and the gravity is in this direction, because it will go down. So what we'll do is we'll take our reference axis downwards. So in this case, because we are free to select our reference frame as we like, so we can take our reference axis downwards. We can take this as our y-axis or x-axis. It doesn't matter what we call it. So this is our reference axis, and the point from which he has dropped it, that point is the origin. Okay. So if this is where it starts from at t equal to 0, then we can see that after some time t, it would have moved along this reference axis, okay, with a velocity v, and its y coordinate would have become y. It started from y equal to 0. So we can see that u would be 0, but its acceleration would be taken as plus g, because our axis is downwards. So we'll take the acceleration with a positive value. Okay. So our displacement will be half gt square. So in this case, we can say the displacement is same as the instantaneous position, and the velocity will be gt. And we can also see that we'll have the relation that v square is equal to 2gs, or we can say v square is equal to 2gy. So these are the three equations that will govern everything. Equation 1, equation 2, and equation 3. So
Could
let's
you
see a
please
simple problem. Yeah.
scroll up for a second?
Yeah. I'll explain the constraints again for this. Okay. So I'll scroll up. Just give me a moment. Okay. So let's look at an example problem first. Okay. So a ball is dropped from a height h above the ground level. Okay. It falls 45 meters in the last second, okay, in the last second of its motion before hitting the ground. Take g equal to 10 meters per second square. So find the height h, okay, the velocity of impact, and total time of free fall. So those who have written the part above, just take down the data of the question and start working on this. Okay. So just imagine this diagram only. This person is dropping the object. Now this height above the ground level, this height is not known. But let's say somebody else on the ground is observing, and what he observes is in the last 1 second of motion, it falls through a distance of 45 meters. So from that, can he back calculate, knowing the value of g is 10 meters per second square? Can he calculate what height it was dropped from and what total time it took to fall, and with what velocity it impacted the ground? These things. Okay.
Yes, sir.
Okay. So just try out this question. I'll also scroll up for those who want to write down or go through the portion above.
So I can't understand the framing of the question. What is written after ground level?
Okay, let me check. A ball is dropped from a height h above the ground level. Okay, then it should be either a comma or a full stop, whatever. It falls 45 meters in the last second of its motion before hitting the ground. You understood that meaning? Okay. So it's dropped from a certain height, but you are
Yes.
observing last second of its motion.
Yes.
In the last 1 second before hitting the ground, it's traveling through a distance of 45 meters downwards. Okay?
Yes.
Piyush, you'll have to check your answer better. I don't think it is correct. In fact, I'll tell you something. If the final velocity is the value that you've taken, then in no 1 second of motion, all of you are getting this. Okay, let me check. Prithvi's answer is a bit closer. Okay. Achha, let me first clarify what do we mean by, when I say like, what is the first second of motion? If a motion has started at t equal to 0, what is the meaning of this term? The first second of motion, what it means? It means the interval of time from 0 to 1 second. Okay, then the second of motion is from 1 to 2 seconds. So like that, suppose the total motion is lasting for n seconds. Then from t equal to n minus 1 to n seconds, this will be which second? It will be the nth second of motion. The third second will be 2 to 3, then the fourth second will be 3 to 4. Like that, the nth second is from t equal to n minus 1 seconds to t equal to n seconds. So
But
for example, Tell me.
That is the duration of 1 second, right?
Yeah, but see, it's an interval of 1 second. So the last second of motion, suppose the total time was n seconds, okay, 0 to n. So the last second of motion is which second? Is the nth second. No? So it is from t equal to n minus 1 to t equal to n.
Right.
You understanding? No? So suppose the total motion is of 50 seconds, then the last second is which one? It is from t equal to 49 to 50.
So the velocity became 45 meter per second, right? Because that
No,
interval is
wait,
of a second.
Wait. No, beta. See, within 1 second also velocity changes, no? Like at t equal to 49, if it started from free fall, what would the velocity be? It would be 450. 490, sorry, it would be, right? At t equal to 50 seconds, what would the velocity be? It would be 50 meters per second. No? So even
Right.
between 49 and 50 seconds, the velocity is not constant. No? It is changing from 490 to 490.1 to 491 to 492, like that. No? Within that 1 second. So every microsecond, every nanosecond, literally every small interval of time also, the velocity is changing because it's a variable quantity. No? The graph of velocity versus time is a linear curve with a positive slope. No?
But since you're saying the last second, doesn't this count as v,
Doesn't
finite
this count as?
velocity?
No, it doesn't, better. So that is the point I'm trying to make. Okay, so I'll explain the question in another way. So let's think like somebody who's observing this motion, what they would tell about it. Okay, that they would tell that suppose it started from this point at t equal to 0 with the initial velocity equal to 0. Then after 1 second, it would be somewhere here below this. And its
Right.
velocity would have become how much? Its velocity would have become g we are taking as 10. So its velocity would have become 10 meters per second.
Yes.
Okay. And its displacement would have become how much? Half gt square. So how much would that be? 5 meters. Okay. Then after 2 seconds, where would the object be? The object would be somewhere here. Okay. It would have traveled more in this second because its velocity is increasing now. So after 2 seconds, the velocity you would see has become 20 meters per second. And the total displacement from above, that has become how much? It has become half into 10 into 2 square. So that's how much? 20. Right. Then after 3 seconds, you would observe that the velocity has become actually how much? The velocity has become 30 meters per second. And it has traveled a total displacement. If you calculate, you'll see it is 45 meters. But this is from the top. Okay. This is not in 1 second. You understanding my point? No?
Yes,
So
sir.
like this, go on in the series, now you'll see at the 4th second, the velocity has become 40 meters per second, and now it has traveled a distance of total distance from the top. And the final 5th second, now I'll tell you how I've done this calculation mentally also. Okay. Because you can do it by formula, but there's a trick method also. T equal to 5 seconds, you will see its velocity has become 50 meters per second. And you will see its displacement has become 125 meters. Okay. Now, in this diagram, if I try to calculate in individual 1 second interval, what is happening, then you'll understand. Okay. So in the first second of motion, what is happening is traveling this much. In the first second, that is from t equal to 0 to t equal to 1. Okay. It's traveling downwards by how much? By 5 meters. In the second of motion, that is from t equal to 1 to t equal to 2, actually how much it is traveling? It's traveling 15 meters, no? Because the total displacement has become 20.
Yes, sir.
Okay, so like that, in the 3rd second, you'll see that is from t equal to 2 to t equal to 3. It's traveling downwards by 25 meters. So like this, when you see, you'll see it's actually the 5th second when it travels downwards by 45 meters. So that means the 5th second is the last second. Because in the last second, it has traveled 45 meters. You getting my point? So here to here, this distance happens to be 45 meters. So that means this is when it's down. Okay.
Yes, sir.
Now, so this I've shown you like a second by second events thing. Okay, we don't need to calculate this way. Okay, we don't need to do the calculation this way. We can do the calculation in a very straightforward way. That t equal to 0, suppose it starts, okay, and suppose it hits the ground at some time t, which we don't know because we don't know this height, and with some velocity v, which we don't know because we don't know. Okay. But we also know that if it was here at t equal to capital T minus 1 seconds, then we know this distance is how much? This is 45 meters. Okay, now this is clear.
Yes, sir.
Okay. So now see this total distance. Let me write this as S1. So S1 kitna hai? It is half g t minus 1 whole square. Okay. This total distance, this is how much? S2 suppose. So this is how much? It is half g t square. So now this 45 meters is actually the difference of these two. Now. So
Yes.
let's write that delta S in the last second. It's like that. Okay. So S2 minus S1 is supposed to be 45 meters. So that's the easiest way of solving the problem now. So half g t square minus t minus 1 whole square, that is 45 meters. So from this I'll directly get that what is my capital T. So you'll see 2t minus 1 is 9. So t is equal to 5 seconds. So as I told you, the total time is 5 seconds. That's why the final second was the 5th second from t equal to 4 to t equal to 5. So this is like the formula based way of doing the question. Okay. So from this information given that in the last second it's traveling 45 meters. Okay. I'm getting, so here I'm assuming total time is equal to capital T seconds. Okay. So therefore the last second of motion is the time interval from t minus 1 to t seconds. So during this time its displacement is 45 meters. So that was the thing I had to catch in the question, right?
Yes,
Yes,
sir.
sir.
So all of you understood now that the total time is 5 seconds, and therefore the last second is actually from t equal to 4 from the beginning to t equal to 5. Is that interval of time from 4 seconds from when I dropped it to 5 seconds. That interval is covering 45 meters. Okay. Now from this, how will I calculate h, the total height?
So S
This
is
only
equal
is
to ut
h.
plus half at square.
This S2 only is h, no? So now I know capital T, so I can calculate. Correct. So kitna ho jayega? 5 into 25, na? So 125. And see in my above diagram also, this was what was happening. When I had done a detailed analysis, like second by second what was happening, we saw that at the 5th second, its total displacement was 125. But at the 4th second, the total displacement was 80. So the difference of the two was 45. See this diagram.
So what goes wrong, sir, if we put the formula v is equal to u plus 80?
Nothing goes wrong, but that formula is fine. V is equal to u plus 80 is fine. But this is, so what this is telling us that velocity at any instant is equal to 10t, right? In this case. But however,
Yeah, so v is not 45.
No, because see that 45 is the distance traveled in one whole second, no? Whereas v is what? Instantaneous velocity, no? You understanding my point, no? V is
Yes, sir, at the
vs by
last
dt.
moment we can't calculate.
Okay.
So this was
But
mistake.
you can use, yeah, tell me without any question.
So the mistake we make is that we equate average speed with instantaneous speed. Like for this 5 seconds, like if we equated v is equal to u plus 80, then we were calculating for 5 seconds or not for that last 1 second, right?
We can't do it that way. That's correct.
Okay, sir.
But see, 1 second is a large interval of time. So one thing I can use is I can use the concept of average velocity. If I ask you what is the average velocity in the last second, then that answer is 45 meters. Meters per second. You're understanding now?
Yes, sir.
So we can't say instantaneous velocity is 45 meters per second because that is how the, see, if you think of the velocity time graph, na, yahan pe, your velocity time graph is like this. The velocity is in the downward direction, but I'm plotting it as v on this axis. Okay. So velocity time graph is this sort of a graph. No? So between 4 and 5 seconds, the velocity is not 45 meters per second. It's actually varying. It is varying from 40 meters per second to 50 meters per second. That's why the average velocity was coming out to be 45. Now you're understanding my point.
Yes, sir.
So instantaneous velocity में 45 नहीं कह सकता हूँ ना, because instantaneous velocity तो at an instant होता है ना. So at t equal to 4 seconds, the instantaneous velocity is actually 40. At 5 seconds, the instantaneous velocity is actually 50. But if you calculate this area, you'll see this area will come out to be 45 because it's traveling that much in the last second. Or if you look at the displacement versus time graph, this is how your displacement versus time graph is looking. Half gt square, so that's 5t square. So it's a graph that is like this, going like this. So at 4 seconds, we saw that displacement was, I had done that calculation for you, it was 80 meters. But by the time it was 5 seconds, the displacement came out to be 125 meters, which means that in this interval of time from 4 to 5 seconds, it traveled how much? It traveled this much. It traveled 45 meters.
Sir, I still don't understand, sir. Then, sir, if I take v is equal to 45 meter per second for 1 second, and sir, I put in the formula, then the time of.
Then that's average velocity, no, beta. See, that 1 second is not a dt, na, it is a delta t.
Yes, sir,
Getting
that
it
part
now?
I got. But sir, after that, sir, what happens to the t? What is wrong with the t that I get?
No, so that the t for what? Like you'll put 45 meters per second is basically what? It is your average velocity, no? It is delta s by delta t. It is v average between 4 to 5 seconds. You understanding my point?
So, sir, it is the velocity we get 1 second before it touches the ground.
No, no. 1 second before it touches the ground, the instantaneous velocity is actually 40. Na?
Then, sir, throughout from the last second to the moment it touches the ground, that interval has the average velocity is 45.
Yes. From 4 seconds to 5 seconds, if you want to calculate the average velocity, yes, that is 45 meters per second. But how is that helping me in solve the problem here? You understanding my point?
Yes, sir, why does it give the wrong time?
Because what you are equating to it is not correct. Na? You are thinking it in terms of instantaneous velocity. Average velocity is not the same thing as instantaneous velocity.
So, but to find the total time, we divide the total distance by total time, by average velocity.
कैसे बेटा थोड़ी ऐसा होता है. एवरेज वेलोसिटी 4 to 5 के बीच में उतना है ना, 0 to 5 के बीच में उतना थोड़ी है. It's an accelerated motion.
About something, missing something.
What are you using? What formula are you using with average velocity? Tell me.
Sir, v initial plus v final by 2.
Okay, chalo. So your velocity at the 4th second plus velocity at the 5th second divided by 2 is equal to 45 meters per second. Okay.
Yes, sir.
Now what? Next, what you'll do? Oh, actually,
Sir,
4
I
and
don't
5
know.
times. So that's the thing. This is not going to help you further. So see, what the approach that you are taking is like this. That suppose the total motion is for t seconds. So the instantaneous velocity at time t is how much I don't know. The instantaneous velocity at t minus 1 is how much I don't know. But I know that the average of these two is how much?
Sure.
It is 45 meters per second. Okay. So that is fine, but it doesn't help me directly. No?
Okay. And sir, v is equal to u plus at formula. That t, sir, what is that t? It's the total time of
That is
motion.
the instantaneous time. It's the instantaneous time. No? So here I'll have to substitute vt as what? G into capital T. You understanding? Because it's the velocity at t. I'll have to substitute v at t minus 1 as g into t minus 1. Okay. And then I'll equate it with 45 meters per second. And now I'll get the value of t from this. No? Understanding? You calculate t from this. Now you'll see you get t as 5 seconds.
Okay, sir. So I equated the time that the object will take to reach that average velocity, wherever that it may be. Okay,
I
sir.
think you're confusing delta t with the instantaneous time. No? You got it now, no?
Yes, sir, I got it.
Okay. Okay. So anyway, there is a method of doing this with a shortcut using average velocity. I'll come to that method. I just don't want to confuse you just now. So let's finish this question, the other parts. Then we'll talk about average velocity again. So you saw how we calculated time, right? And how we calculated height. Now the final velocity with which it hits the ground, that will be what? It will be the velocity at 5 seconds because the total time is 5 seconds. Okay. So the impact velocity with which it hits the ground, that is nothing but velocity at t equal to 5 seconds, because we know that capital T is equal to 5 seconds. So that will become 50 meters per second. So it is hitting the ground with a velocity of 50 meters per second after falling through a height of 125 meters through a time of 5 seconds from when we dropped it. So that becomes the conclusion. Okay, so hope this question is clear, people.
Sir, can you give us 1 second?
Yeah. Okay, so I'm going over my method again. So what the question said that last 1 second may it traveled 45 meters. So let me assume the total time it traveled is capital T. And in the total time, its displacement is S2. So S2 is equal to half GT squared, this equation. Total time of flight before it hits the ground is T. So in that the displacement is S2. But 1 second before capital T, what would the displacement be? It would be this. So this is at 1 second before capital T. So now between this time and this time, that is the last second of motion, the displacement is how much? 45 meters. So S2 minus S1 should be 45 meters. So from that I'm calculating capital T. And once I calculate capital T, rest is formula based, because I know that velocity as a function of time is GT, displacement as a function of time is half GT squared. Here the time T is the time from the beginning, from T equal to 0 to that instant.
Sir, I didn't get the impact velocity part.
Impact velocity is the velocity just before it hits the ground. No? So now we know that when does it hit the ground? Capital T, and capital T we calculated in 5 seconds.
Yes, sir.
So what is the velocity just before hitting the ground? It's acceleration due to gravity into 5 seconds. No? So that's how we can. So what are our 3 standard equations of free fall starting from rest? That V is equal to GT, S is equal to half GT square, and V square is equal to 2G S, like this. Okay, where S is the downward displacement. Okay, now let's move to the second case of this kind of motion, downward motion due to gravity. Okay. Now this time, instead of releasing the object from rest, suppose what we're doing is we are throwing it down. Its motion is straight line downwards only, but the difference is it has an initial velocity. So it is thrown down with an initial velocity u at t equal to 0. Okay. And let us say the height from which it is thrown from the ground is h. So now let us say that at some in between time it has reached here. Okay. And then finally, continuing down, it hits the ground at some time capital T. Okay, so now we want to find, first of all, express E and the displacement S as functions of time. We take the acceleration due to gravity as G, and then secondly, find capital T, time of impact, and let's say Vi, which is the impact velocity, the velocity with which it impacts the ground. Okay. Now for this example, we will take the value of U as, let us say, 20 meters per second. Okay, and we will take the value of this thing H as G, of course, we will take as 10 meters per second square. Okay, so we will take 300 meters. Yeah. Okay, so let's try this now. So this is the second case. It is thrown down with initial velocity. Last case was when it was just dropped from rest. We'll do one more thing. We'll also plot the rough graph. V versus T and displacement versus time for this motion. Now, mind you, in this motion, we are solving it only up till the time it hits the ground. We are not really concerned what happens after that. Maybe the object just remains buried in the ground or it bounces off or whatever happens. We are not concerned with that. Okay. We are just concerned with the motion happening between the time we threw it down at t equal to 0 till the time it hit the ground at capital T. So now we have to get the numerical values of capital T and impact velocity, whereas V and S in the first part you have to get as functions of time. Okay, this is direct application of uniform acceleration 1D motion. Okay, I have got one set of correct answers. But some of you, I think, are making a mistake of some factor of 10 somewhere. Just check. Okay. Anyway, so I'm putting up the answer for the first part. V as a function of time will be much 20 plus 10t, but the direction is downwards. Okay. And the displacement as a function of time will be 20t plus 5t square. Again, the direction is downwards. Okay. Now you can see that just using these two equations only, you can find the answer to these two. It's not so difficult. Okay. You should be getting t as 6 seconds. Okay. And the final impact velocity as 60 meters per second. Oh, sorry, as 80 meters per second. There's initial velocity. Yes, good. Janvi, Mansi, Aparna, all of you got this correct.
Sir, what is the height?
300 meters, beta. H is 300 meters. See, here it's given. H is 300, U is 20 meters per second, G we have to take as 10.
Yes.
Okay, so that's very good, Nidish. So I hope all of you are understanding how this comes. So again, it's once you have got your axis system and on the reference frame properly decided, you'll see there's no problem. You take this as your origin and you take this downward direction as your axis. You can take this as the displacement axis or y axis or whatever. So in general, you can see you'll have to write your initial velocity as plus 20 because it's in the downward direction. That's the positive direction. And most importantly, your A will also be plus G, or in this case, plus 10 meters per second square, but because that's also in the downward direction. I've taken my axis in the downward direction. That's why. So once you get that, just use the formula. So V is equal to U plus 80. So the first part is just like this. So the velocity at any instant is 20 plus 10t. The displacement at any instant is accordingly now 20t plus 5t square. So these are your fundamental equations, and you have that one also, that V square is equal to 20 square plus 20s. If required, you can use this third equation also. Okay. For example, this impact velocity we can calculate from the third equation also. Okay. But anyhow, so now let's come to the second part. Now we can see that the height is given to us as 300 meters. So what this means is that at time capital T, it impacts the ground. Okay. So that means what should happen? S should become equal to H. So substitute this information. This information is now substituted in which equation? The relation between S and T. That's the second equation. So H should be equal to 20 capital T, or if I write it in parametric form, H should be equal to UT plus half GT square. So in numerical value, it becomes 300 is equal to 20T plus 5T square. So this becomes a quadratic equation. From this, we'll get time. Now, there's an interesting explanation why one of the roots will be negative, and I'll give you the explanation of that root also later. But at the moment, we'll just say that, okay, time cannot be negative because we're starting a stopwatch from t equal to 0 in the forward direction only. So we'll only take the positive root. So this quadratic equation just divided by 5 becomes t square plus 4t minus 60 is equal to 0. Okay. So you'll see that this gives you one root as 6 and the other root as minus 10, correct? Sum of the roots is minus 4, product of the roots is minus 60. Okay. So we will take this root, we will reject this. Okay. Oh, now I realize why some of you got the answer wrong. You must have got the roots as minus 6 and plus 10. Okay, so be careful about these things. Okay. So once we know this time, now the impact velocity is quite easy. We can see that the impact velocity is the value of velocity at t equal to capital T. So it is 20 plus g, that is 10 into 6. Okay. The final impact velocity will be u plus gt. So 80 meters per second. So it hits the ground at 80 meters per second at the time of 6 seconds. Or alternately, you can also use this, that v impact square is equal to u square plus 2gh. See this also. Now it's a speed, no? It's the magnitude of a velocity. So we won't take the negative root, we just take the positive. This is from third equation of motion. This is from first equation. So I have all these options. Okay. Now let's talk about the graph. It's a very simple thing. We just have to convert those equations into graphical knowledge. Right? So v is a linear function of time, so it's a straight line graph, and s is a quadratic function with the increasing slope. So it's like that kind of parabola we had discussed that day, where u is positive and a is positive. So my s versus t. The only thing is that the graph will abruptly end here when it hits the ground. Okay, so this function will not proceed. We'll just stop at, what was it, 6 seconds, when it reached a displacement of 300 meters. So in general, this is this function. It is 20t plus 5t square. Okay. Whereas my velocity time graph is also ending abruptly like that, but now this has a u and it has a positive slope. So it's like this. Let's say this is where 20 is. And it ends at a velocity of 80. So it accelerates from 20 all the way to 80 in a matter of those 8 seconds. Sorry, in the matter of those 10 seconds. Sorry, in the matter of 6 seconds. Sorry. So another interesting thing you'll see here is that if you calculate this total area, you should get 300 meters. See this area? It is half sum of parallel sides into distance between them. It checks out that you're getting 300 meters. That is the total distance displacement it's traveling. Whereas at any arbitrary instant here, if you calculate the slope of the tangent, it should give you the instantaneous velocity. I mean, these are obvious things. We don't require this for this question. You can see it's 20 plus 10t. So that is a relation between these two graphs. This one's area is that one, and that one's slope is this one. Okay, so people, I'm guessing all this is quite clear. Now we come to the slightly more tricky part of vertical motion. That is when we throw something up, or in other words, vertically upward projection. Okay. So till now we are discussing about free fall. Now we see vertical projection. That means we are projecting something, but with a vertical velocity. That means an upward velocity. Now, of course, keeping in mind here, the velocity should not be so much that it goes to a great height of thousands of kilometers. Even up to hundreds of kilometers is fine because G will remain uniform. But so if we project something with a upward velocity of u at the time t equal to 0, then what we know is that it has a decelerated motion as it goes up, but then also it stops and then comes back down. So this is that case where distance and displacement will not be the same. When we are talking about free fall, distance and displacement were the same because it was not switching direction. If it bounced from the ground, that's a different matter, but we're not considering that. We're only considering up to when it hits the ground. But in this case, it's going to be different. Okay. So G is like this. So normally what we do is we always take the axis in the direction of initial velocity. So if you like, you can take the axis downwards, but it will just make your equations a little awkward. So what you should do is you should take your axis in the upward direction. You take it as your y-axis or your displacement axis or whatever. So taking the axis upwards, your sign convention will become that my initial velocity is plus c, but my acceleration will become minus g. This will be the sign convention because my axis is upwards. So my v as a function of time. So at some time t when it is here, let's say, if it has an upward velocity, assuming this, so v will become u minus gt, and s will become ut minus half gt square, and in general v square will be equal to u square minus 2gs. Okay. So mind you, what will happen is that it will also reach this position on its way down. So at some later time, let's say some t equal to t prime, it will be like this. You'll have a very symmetric thing. If when it crosses this position, it'll have the same magnitude of velocity but going downwards. Okay. So there's a lot of symmetry in this motion. The upward journey and the downward journey, they are just like mirror images of each other, and they're also like as if you're running time in backwards. So I'll explain that with equations also. Okay. So these are the three equations that we'll be using. Okay. Now using these standard equations, we calculate some standard quantities. Okay. So the first is the maximum height or maximum vertical displacement. So this is one parameter that we calculate, that is h. And the other parameter that we calculate is the total time of motion, that is start to impact on the ground. Okay. So that is like assuming it comes back here, and actually in this case he's thrown it from somewhere above the ground, so we'll have to consider when it comes back to the same level. Okay, so that time is capital T. Okay. So these two things we need to calculate, and these two come as direct formulae from the above three equations because h. So for h, use the fact that h is equal to maximum displacement. So V is equal to 0 when S is at its maximum value, because V is what? ds by dt. Okay, so that local maxima minima thing, okay, you realize that when it reaches the topmost point, that is at this point of time over here, what will happen is momentarily its velocity will be 0 and its displacement would have become the maximum value, or that would have become the height h that we calculated. Okay, so using this fact that V is 0 when S is equal to maximum value, we substitute this in equation 3. In equation 3, put S is equal to H when V is equal to 0. So get 0 is equal to U square minus 2GH. So that very easily gives us the formula for the maximum height, U square by 2G. So don't have to really memorize this formula. You can just remember it this way also. Another way to remember it is that kinetic energy is converted to potential energy. So the initial kinetic energy is converted to the maximum potential energy at the top. So half mu square is converted to mgh. All the kinetic energy is converted to potential energy. So u square is equal to 2gh. You can see from this. On this. Okay. So don't really need to memorize this formula. Okay. And the second thing is we need to calculate capital T. Okay, so for capital T, what we do is we use the fact that at time t equal to capital T, what is the displacement? It becomes 0 because it is back to starting position. In my diagram, I have shown it alongside, slightly beside it, but actually it's the same point from where it started, because it will retrace its path perfectly in the straight line. So it exactly comes back to where it started from. Okay, so it's back to starting point. So the net displacement should be 0. So now from equation 2, substitute S equal to 0 when T is equal to capital T. So that equation will become, second equation above, you can see that 0 is equal to ut minus half gt square. So that will give me that T into u minus half gt is 0. So obviously T equal to 0 is not a root that we'll consider because that's the initial time. Whereas the second one, u minus half gt is equal to 0. That will give me the correct formula for time of flight. So 2u by g. For this also, there's a shortcut way of remembering the formula. I'll tell it to you later. I mean, in just a few minutes. Okay. So first note down the derivation of these standard parameters. So when we throw an object vertically upwards with a speed u, the maximum height to which it climbs is u square by 2g. And the very easy way to remember it is that kinetic energy is converted to potential energy. So that half mu square is equal to mgh. Forget about kinematics. Just remember this like a work energy formula. Okay. Of course, I have shown the derivation from kinematics also. Okay. But just a quick way to remember that when it reaches the highest point, it's at rest. So all the initial kinetic energy has been converted to mgh. So it's a very easy thing that h becomes u square by 2g. And the other is the total time it takes to come back to where it started from. Okay, so that total time is given by the formula 2u by g. Okay, so just make a note of this. We'll discuss further.
So what have you written in the diagram, like under axis, like y, what, and then
You can write it as y or s. I mean, you can name the axis as your y-axis or your displacement axis s. It's one and the same thing, right?
okay, sir, okay.
You can name it the x-axis also for that matter, x, z, whatever. Just the important thing is the sign convention. The upward direction is positive. Okay. Now, few more things to keep in mind before we come to questions. At the highest point, that is when the displacement is equal to h, okay, where of course we know h is equal to u square by 2g. The velocity is 0. Okay. The time is actually half the time of flight. And this you can understand from the first equation of motion, that v is equal to u minus gt. So you can see that v is equal to 0 at t equal to u by g. And total time above we had seen was this. So you can see. So this is also an easy way to remember the total time of flight, because from this equation you can see the velocity is becoming 0 at u by g. So that's the time taken to go up. Now the time taken to come down will be the same. So the total time is double of. Okay. So this thing is important, that at the highest point, these three things, the instantaneous velocity is 0, the time is half of the total time of the motion, and the displacement is obviously the maximum height, which is this thing. Okay. The other thing is that the upward journey, you can say, okay, and downward journey are symmetrical. Now this point that I'm writing here, that they are symmetrical, we will support this with equations and some logic also.
Sir, is there any special case in which capital T is not 2 into small t?
I mean, the total time is not like half of the, I mean, total time is not double of the time taken to go up.
Yes, sir.
Not special case in motion under gravity. But yes, if along with gravity you take into account there is significant amount of viscous force or air drag, then that will happen. Then the upward and downward motion will not be symmetrical.
Okay, sir.
Okay, and it's a very easy way to understand why that is the case. Because see, air drag, the force acts in which direction? Opposite to velocity, right? So if
Yes.
something is moving up with a velocity v, then the direction of air drag force will be what? It will be downwards. So let's call that Fa. And of course, weight is also downwards. Okay, whereas when that same thing is on its way down, okay, air drag force will become in the upward direction and the gravity is in the downward direction. So you can see the acceleration is not symmetrical, or the net force is not symmetrical. While coming down, it has a smaller magnitude of acceleration compared to the deceleration while going up. So then the journey will not be symmetrical.
Yes, sir.
Okay.
Sir, then if
Yeah.
it is the ball is released from a point below the x-axis and lands on above a platform.
Yeah, we'll discuss those also. But basically, you have to use these fundamental equations. Okay. Now, when it lands on the platform, it could also be a situation like this, that you threw it from the ground and the platform is here, let's say. Okay. Now, let's say there's somebody to catch over here. So one is that that person can catch when the ball directly reaches there. Or another is that the ball could actually go up a bit higher, stop, then come back. And on its way down, the person catches it. So there are two different instants of time when that person has the opportunity to catch it. So all those things, how we'll calculate that, at what time he can catch, what is the displacement when he catches, what is the distance traveled. So all that will come from the analysis of the three fundamental equations. You're understanding now?
Yes, sir.
Okay. Okay. So actually this point of symmetry will help you understand ways of solving these type of questions also. So let me discuss this symmetry with an example. Or actually we'll start by discussing the graphs, so that symmetry will be evident in the graph. So when you look at V versus T graph, for this case, V is equal to U minus GP. Okay, you'll see that again, I'm taking a limited amount of time in my graph. The time is only from when it started till it came back to the ground, or till it came back to the starting point. So when I take that limited amount of time, you will see that my U versus, my V versus T graph will be like this. The part above and below will be symmetrical. If this is capital T, then the time when the velocity becomes 0 is exactly T by 2. And if it started with a velocity of plus U, it will come and hit the ground with a velocity of minus U. So same magnitude it hits with. So you can see that symmetry, that at some particular time here, which is, let's say, T equal to T1, if the velocity is some V1, then at some particular time here, which will be like T2 equal to capital T minus T1, the velocity would have become minus V1. Okay. So for example, if you are observing the motion 2 seconds after start, and then again you are observing the motion 2 seconds before it hits the ground at the end, you'll see that they'll have symmetrical velocities, plus V1 and minus V1. So that's one point of symmetry. The other is when you look at the displacement time graph, you again see that symmetry. S is equal to ut minus half gt square. So this is that kind of parabola now. Okay. So just recall how we had plotted the various types of parabolas that day, in the last lecture. So it was quite a bit of time before. So this is a parabola which has negative coefficient of t square. So it should be downward opening, right? And the roots of this parabola are what? T equal to 0 and t equal to 2u by g. And if you just factorize it, you can see ut minus half gt square be written as t into u minus half gt. So the roots are t equal to 0 and t equal to 2u by g. So it makes sense altogether now. One of the roots is here, 2u by g. Okay. And the graph should be, now obviously we will not take negative displacement, so we are not plotting the entire parabola. It will be like this. And obviously the vertex of the parabola, which is the where the displacement is maximum, is at the midpoint. So if this is capital T, this is at, sorry, this is T by 2 or U by G, and this is where the displacement becomes maximum. So here also you can see that if it has a certain height from the ground at some time T1 on its way up, then again it will repeat at that same height S from the ground at some new time, and that new time will be symmetrical. It will be T2 equal to capital T minus T1. So if it was certain height from the ground 3 seconds after start, then 3 seconds before it comes back to the starting point also, it will be at the same position. And it will have a negative velocity this time, because here the slope is positive, here the slope is negative. The two slopes are symmetrical. So this slope in this graph was V1. This slope in that one is minus V1. Okay. So this is how the symmetry of the upward and downward journey works.
So sir, velocity at t and t minus 1, t minus t are equal and opposite.
Velocity at T1 and capital T minus T1, yes, they are equal and opposite. That's correct.
Yes, sir.
So, so suppose, my total time of flight is, let's say capital T is 20 seconds. Then the velocity at 2 seconds and then again at 18 seconds, they'll be symmetrical. The velocity at 3 seconds, then again at 17 seconds, 17, they'll be symmetrical.
Yes, sir.
Okay.
Sir? Hello?
Yes, madam.
Sir, so if we see velocity, if we take it instead of taking the motion from, if we throw it from the ground and it falls back as a going up and down, if we just stretch it out as a straight line, then when we say that at like you said, third and the 17-second velocity is same, but it will be the opposite.
Velocity is not same, beta. Speed will be same, but the velocity is directly opposite. One has to be very technical. Velocity is a vector quantity. So
the velocity becomes opposite, right?
Becomes opposite, yes.
So the same doubt I have with acceleration.
No, acceleration is always the same. Just think of the vector. When you draw the acceleration vector as an arrow, on its way up also, how that arrow points? It points towards the ground.
Yes, sir.
On its way down also, it points towards the ground.
Yes, sir.
So it's never changing.
So, sir, but for a mathematical equation, how will we depict that it is acting downward? So, if the ball is going upwards, the acceleration will subtract from the velocity, and if it's going downwards, it will add to the velocity. So, we'll have to change the sign.
See what is happening. I'll explain to you. See, while coming down, what is your velocity's algebraic sign? Negative, no? Because I've taken the axis positive upwards.
Okay, yes.
And what is your acceleration sign? It's minus g.
But sir, don't we usually take since gravity is always is pulling downwards, that's positive, and when it goes, okay. So I guess in 10th we learned it like that when we throw it upwards, we take A as negative.
Yeah, but that's correct. Okay, but that will apply even on the downward journey. The thing is, like, you should not change the sign convention in between a journey. Like, if the same ball is going up and then coming down, you can't switch your axis in between. That one time you took upwards as positive, then on the downward journey you took downwards as positive. Then you'll have to draw two separate graphs, because your reference frame is changing. You're following my point, beta? So if the entire motion, like suppose the motion is for 20 seconds, then for 10 seconds it's going up, then from 10 to 20 it's coming down. Now if I want to show that entire motion of 20 seconds in the same graph, then it should be with respect to the same reference frame. No? So throughout that motion, so see, that's what I'm saying. No? Your axis is pointing in which direction? Upward direction, right?
Yes.
So if your axis is upwards, then how will you represent a vector which is pointing downwards? It has to be a negative quantity, no?
Right.
So your A will always be minus 10 or minus G.
Yes. Yes.
You understood, no? So the A is constantly minus 10. A is not changing over here.
So the velocity becomes positive and negative too.
Yes.
Acha, okay.
So on the way up, velocity is positive and acceleration is negative. So they are opposite, no? Whereas on the way down, velocity becomes negative and acceleration is already negative. So they're in the same direction.
Yes, sir. Okay.
And see, if ever you get confused with the sign convention, you can always do one thing. Go to vector notation. Just use the unit vector. So on the way up, your velocity is something into plus j cap and the acceleration is something into minus j cap. So obviously they are opposite, no?
Yes, sir.
On the way down, your velocity is a negative j cap quantity. Your acceleration is also negative j cap. So there's no confusion. They're in the same direction.
Got it, sir.
So like this is often it gets confusing while solving questions. So you have to be very careful about sign convention. Okay. And the thing you should remember is that within one problem, don't change your axis. Like be consistent.
Yes.
Either you take the upward direction as positive or the downward direction as positive. It doesn't matter. But don't switch in between in the same question or in the same analysis.
Okay, sir.
Okay. Okay, so now let's look at a quick question based on this. Okay. So a body is projected vertically upwards. Okay. At velocity u at time t equal to 0 and reaches a maximum height of let's say 125 meters. Okay. Take g equal to 10 meters per second square. So first of all, find the initial velocity, total time of flight, this is called actually. Now this is just a term that is used. What we mean by total time of flight is basically total time to return to starting point. That is what is generally meant by the term total time of flight. So capital T that we have to find. Okay. We have to then also find the displacement and velocity at t equal to 5 seconds, 6 seconds, and just a minute. Yeah, make this 4 seconds, 5 seconds, and 6 seconds. And we also have to find the distance traveled from t equal to 0 to 4 seconds, 6 seconds. So just try this out. We'll learn a lot of things about vertical motion with these type of questions. So you can see that it's an indirect question. Initial velocity is not given to us, but some hint is given to us about it because the maximum height is given. Yes, Mansi, very good. That's correct for the first part.
Done, sir.
Okay, very good. So people have sent me answers which are mostly all correct. Okay. So first of all, we'll be getting the initial velocity as 50 meters per second, and the total time will come out to be therefore 10 seconds. 5 seconds going up and 5 seconds coming down. Okay. And that will mean that after 4 seconds, my displacement will be 120 meters. Whereas at 5 seconds, it will reach the maximum height actually. So the displacement will be the maximum height, which is 125 meters. Interestingly, at 6 seconds, the displacement is back to 120 meters. Whereas when we talk about the distance traveled from 0 to 4 seconds will be 120 meters. But from 0 to 6 seconds, the distance traveled will become 130 meters. Because it's going up 125 meters and then coming down 5 meters. Okay. So I see for some reason, some of you have got that last answer wrong, that 130 meters. Many of you got correct, of course. Very good. Aparna, Prithvi.
Sir, displacement at t is equal to 6 seconds should be minus 5 meters, no?
No, because see, displacement, we always consider when we say displacement at a certain time, we mean from 0 to that time. Na? So 0 pe kahan pe tha? Ground pe tha na? So compared to the ground where it is at 6 seconds, it's at a height of 120 meters. Na?
Yes, sir.
Okay. Whereas if I ask you something more specific, like find the displacement from t equal to 5 to 6 seconds, then the proper way to answer this would be that the displacement is actually minus 5 meters, or I could say that the magnitude of the displacement is 5 meters, but the direction is downwards. Okay, but here this is the this thing now, displacement at this time. So when we say at this time, it always means from the t equal to 0, from the starting to that time.
Yes, sir.
Yeah, this point is clear, I hope. Yeah.
Yes.
Okay. Now see, I'll tell you the easiest way that I can figure out of doing this question. One is that, of course, start with the formula. So what is given to you is maximum height. And of course, we know the value of G. So from this, what we can calculate? U square by 2G is equal to H. So we can calculate U. So it's 50 meters per second. Now, once you got this, now don't think in terms of formula. I'll tell you an easier way. Just think in terms of velocity time graph. Everything will come from that. Achha, we have to find instantaneous velocity also at this time. So you'll see that at this time, the instantaneous velocity is plus 10 meters per second going up. Okay. At this time, the instantaneous velocity is 0. At this time, it is minus 10, or basically it's coming down. Okay. Now, tell you why this makes it very easy. Because the linear graph itself will show you the velocities at various times, and the area under the graph will tell you displacement. And if you just add the areas as magnitudes, you will get the distance instead of displacement. If you add them as algebraic quantities, then you will get displacement. Okay. So this is 50 in meters per second. This is 10 seconds when it's becoming minus 50. And 5 seconds is becoming 0. Okay, so for example, in this itself, you can see now that at 4 seconds, you can see that it will be 10. Okay. And therefore, you can see at 6 seconds, that symmetry thing I was telling you about, it will be minus 10. So you can also understand that the displacement from 0 to 4 is this area. This is the displacement from 0 to 4, but that is also equal to the displacement from 0 to 6. Because what happens is that whatever displacement is happening from 4 to 5 is cancelled by the displacement that is happening from 5 to 6. So displacement from 4 to 5 has the same magnitude as the displacement from 5 to 6, which is 5 meters. Okay. That's why total distance will be the sum of these two triangles, but the displacement will be the larger triangle minus the smaller triangle for 0 to 6. So you can just use, the graph to calculate these also. Now, for example, in this question, once you got the initial velocity, suppose I asked you that at what time is the displacement equal to, let's say, 105 meters from the ground. So first thing you should understand that this time will not be unique. There will be two times. Okay, because your displacement versus time graph is going to be this type of parabola. No? So there will be two instants, one on the way up and one on the way down. So this is 125. So let's say 105 is somewhere here. So there will be two times when this is happening. If this time is T1 and this time is T2, you can see these two times will be such that T1 plus T2 is equal to capital T. Two such times. So how we'll calculate this is we'll substitute 105 is equal to 50t, that is ut, minus half gt square, 5t square. So t square minus 10t plus 21 is equal to 0. So we'll solve this for time. I think what you should get the time as is 3 and 7 seconds. Just check.
Yes, sir.
Yeah. It says. You can see here that T1 is 3 seconds and T2 is 7 seconds. So at T1, the displacement is 105, but you'll also see that the velocity is going to be plus 20, that is upwards. Whereas at T2, the displacement is again 105 meters, but the velocity will be negative. It will be minus of 20 meters per second. So that symmetry thing I was telling you about, that also works here. Okay. So now you're getting an idea of those type of questions. Now, suppose I told you that somebody is thrown a ball from the ground with a speed of 50 meters per second. And another person is standing such that his hands are at a height of 105 meters. So at what point of time he can catch the ball? So he can catch it either at 3 seconds or 7 seconds. 3 seconds if he catches it while it's coming to him from below. And 7 seconds if he catches it, if it's gone past him and then on the way down.
Sir, can you scroll up?
Yeah, sure. Okay, this is fine, beta.
Yeah. Oh, I wanted to see the graph.
Yeah. Okay, so this is the full solution now. Okay, so this question is done now.
Yes, sir.
Okay. Okay, now for not just vertical motion, but any motion with uniform acceleration, any 1D motion with uniform acceleration, we will see one useful trick apart from the 3 equations and all this. For any uniformly accelerated 1D motion, average velocity in a certain time interval is the arithmetic mean of the velocities, instantaneous velocities in that. Okay, so this is average velocity from t equal to t1 to t2, and in this v1 is equal to velocity, instantaneous velocity at t equal to t1, and v2 is equal to instantaneous velocity at t equal to t2. Now the proof of this is very simple. You can just think of it from the graph only, because your velocity versus time graph is a linear graph. Okay, so your displacement is always that area of trapezium formula. So from that itself you'll understand. So whether the graph has a positive slope or a negative slope, it doesn't matter. If the velocity versus time graph is like this, v equal to u plus at. So let's say at some time t1, my velocity is this value v1, and at some time t2, my velocity is this value v2. Okay, then what is the total displacement from t1 to t2? Is this area. Okay, so this area represents the displacement from time t1 to t2. So that area is how much? Half sum of parallel sides. So that is v1 plus v2 into the distance between them, that is t2 minus t1. This you can see here, this is t2 minus t1, this time interval. Okay, this is v2, this vertical line is v1. Okay, so now what should be the average velocity during this time? So v average from time t1 to t2 is the displacement from time t1 to t2 divided. So there you can see it is half of v1 plus v2. So something very simple, but now in certain questions, this can be used as a very effective way of solving rather than using the standard equations. Unnecessarily, the standard equations will give you a very lengthy solution, whereas using this, but then at the same time, you have to be able to judge that which type of question you will use this formula in. So just make a note of this, and we'll look at an example question also. So ball is thrown up, and it covers at upward displacement of 80 meters from t equal to 3 to t equal to 5 seconds. Okay. So it is thrown up at t equal to 0 and covers an vertical displacement, upwards displacement of 80 meters from 3 to 5 seconds. So from this, we want to find its initial velocity, and I mean, once you find initial velocity, you can find everything else. So just let's find the initial velocity. Okay, very good. Aparna, Aryan, Prithvi. So first, I'll take you through the normal approach. Okay, so let's assume that at t equal to 0, my initial velocity is some u. Okay, so my displacement after 3 seconds should be 3u minus 5 uh, into 9, right? I'm taking g as 10. Sorry, I should have told you before, but just assume it's 10. And this is at 3 seconds. Okay, and at t equal to 5 seconds, my displacement would have been 5u minus 5 into 25. So this is 3u minus 45, and this is 5u minus 125. Okay, so my displacement from 3 to 5 seconds is displacement after 5 seconds minus displacement after 3 seconds. So that you can see will become 2u minus 80, and that is equal to how much? 80. Okay, so this is one way of doing the question. Okay. Another way of doing the question is, see, if u is this, then at t equal to 3 seconds, what is the velocity? It is u minus 30. Okay. And at t equal to 5 seconds, what is the velocity? It is u minus 50. So what is the average velocity from 3 to 5 seconds? It is u minus 40 in दोनों का mean. Okay, and that should be equal to the displacement in 3 to 5 seconds divided by the time interval. So that is 80 divided by 2. So u minus 40 is equal to 40. So this is also a very efficient way of solving this type of questions.
Sir, I have a doubt.
Yeah.
Sir, I solved it some other way. Sir, I took 80 is equal to some u dash. Sir, I took the difference between T3 and T5. So I got u dash is equal
But
to.
how did you equate 80 with some u dash? Because you tell me 80 meters is the distance traveled in a 2-second interval. No? How are you relating it to instantaneous
Not to u
velocity?
dash. Sir, I related it to 80 is equal to u dash plus half into 10 into 4. And that u dash is the velocity after 3 seconds.
Okay. So it's like this. So you're taking the velocity after 3 seconds to be u dash, right?
Yes, sir.
So then what is the 80 meters? It is the displacement in the next 2 seconds, no?
Yes, sir.
So then 80 should be equal to what? It should be 2 u dash minus 5 into 2 square. You understand?
Minus.
Because it's upwards only, no? So G, okay. So from this you will get your u dash, and your u dash will come out to be 60. Sorry, it will come out to be 50. U dash will come out to be 50 meters per second, which will again show you that your u is equal to how much? 80, because this is at 3 seconds. No? U dash is at t equal to 3 seconds.
Yes, sir.
Right? So yeah, you can do like this also, or you can just do the question this way also, that see, you take velocity at 3 seconds as u dash. Okay, so velocity at 5 seconds is u dash minus 20. Okay, and their mean should be equal to how much? Their mean should be equal to 80 meters in 2 seconds. Okay, so u dash plus u dash minus 20 by 2. This term should be equal to how much? It should be equal to 40. So from this you will get u dash as how much? You get u dash as 50 meters per second. And once you know u dash is 50 meters per second, you can back calculate and see that u will be equal to 80 meters per second, because at 3 seconds the velocity is u minus 30. So that's another way of doing it. Okay, so this is clear, no?
Yes, sir.
Okay. Okay, so we'll conclude with vertical motion here today, and like as I said, most likely we'll have a lecture tomorrow morning, so not too much time, probably not even 12 hours of time before the next lecture. Just one last thing I want to finish off with. So if we are looking at the velocity versus time in a vertical projection, and that graph looks like this, as we are discussing. So it goes from plus u to minus u in a time frame of capital T. Then how will the speed versus time graph look? If I want to convert this to a
modulus function like that.
Yeah, so you just apply the modulus function. So take a mirror image of the part which is below. So this is my speed. Okay, so speed versus time graph will look like a inverted V shape or whatever. Actually a V shape in this case. So the speed increases back to u. And similarly, if you are comparing the displacement versus time graph with distance versus time graph, now put some thought into this. How will the distance versus time graph look? How you have to modify the displacement graph so that you convert it to distance?
So distance will be triangle and the displacement will be 0.
But as a function of time, remember displacement was a parabola, no?
Yes, sir.
So now obviously distance cannot be like this, because distance cannot reduce. It either becomes constant or it. So how we have to modify this now? This is displacement versus time. So This is displacement. Now, if I convert this to distance, now here, like, it's not correct to say that distance is mod of displacement. It's a little bit different than that.
Sir, we'll have increasing graph, sir, from t/2.
Yeah. So what we'll have to do is we'll have to invert this graph from t/2. Up to t/2 is the same. Then momentarily it stopped at t/2. Okay, and then instead of coming back, now is the distance continues to increase. So you invert this graph. Okay, so it's like you take a mirror image of this section. It would have been like this. You just take a mirror image of this. So this is what is happening at capital T. So whatever maximum height it was going to, now u square by 2g, the total distance is double of that. From 0 to capital T is 2 times u square by 2g. So I mean, you don't have to memorize the graphs or anything. You just have to understand how to apply the concepts of linear graphs to velocity time graphs and apply the mod to convert it to speed. And just remember the tricks I told you for plotting parabolic graphs or quadratic functions. Those tricks are more than enough to, very quickly visualize these kind of displacement time graphs and do any analysis related to that. Whether it is a question that is given to you in graph form and you have to interpret it, or you are given the values in the question and you have to select the correct graph, or you're trying to solve the question by using the graph, whatever be the case, okay, you will not find it difficult to do the graphical analysis. You've done enough in calculus. Okay. So people, with that, we conclude today's session. As I said, like, we'll wait for the timetable to come. Okay, Bhavik, I will try to send the recording by tonight because it takes a bit of time for the recording to process. About, I mean, anything from few minutes to an hour or so. So I will try to send it tonight. And like I said, let's wait for the timetable, but most likely we'll have the regular timetable. So tomorrow we'll be meeting again. So good night, people. Wish you all the best. Thanks for attending.
Two things.
Bye, sir. Thank you,
Thank
sir.
you. Bye.
Bye.
In starting,
Bye, sir. Thank you, sir.
Tomorrow.
Bye, people.
sir, like in first question of today's class, you said now that there's a trick also to do it. So,
Sorry, but I didn't get what you were saying.
sir, I said that in first question of our today's class, so you said now that there's a trick to do that question also. So you didn't tell us that trick. And one more thing, that the time of 6 and minus 10 seconds, and you said that we won't consider that minus thing. So
Yeah.
you didn't tell us those two things. So.
Okay, I will take some examples tomorrow and explain what is the significance of that negative time root that we get. Okay, but you understand that we cannot take that as a root for some answer, no? Because that time has to be in a positive value.
Yeah. So that's like common logic.
I will tell you how to interpret that negative time in a different way tomorrow. Okay.
So can you send the notes by tonight?
Yeah, notes I'll send immediately. I'll send the recording also. Okay.
Yeah. Thank you, sir.
Okay.